Alright, this is Ken Roosevelt. We're talking about normal approximation of binomial distribution. This is covered in 6-4 in your book, beginning on page 338. On page 340, a procedure table is provided, which gives 6 steps for doing a problem like the one you see above. The first step is to check whether the normal approximation can be used. We know that a coin flip very rapidly, if you repeat the trials, has a distribution that looks approximately normal, but that's a 50-50 shot. As P or Q pushes to either extreme, gets closer to 0 or 1, the distribution can be skewed for smaller sample sizes. So what you want to do to check whether a normal approximation can be used is to make sure that n times p and n times q are both greater than or equal to 5. So for a coin flip, n times p and n times q would both have to be greater than or equal to 5, means you can't approximate normal, or you can't use a normal approximation to a coin flip unless you're flipping at least 10 coins. 50-50 shot, n, 10 flips is a sample size of 10, and a 50-50 shot would give you n times p equals 5 exactly, and n times q equals 5 exactly. So you always want to check, does n times p and n times q are they both greater than or equal to 5? And clearly here, 56% of 50 is bigger than 5, and so is 44%. So we don't have to worry about that. And in fact, in ALEKS, when you do these, you can almost assume step 1 is always a yes, because they're not going to give you one you can't do, because then they can't test you, right? So step 2 is find the mean and the standard deviation. The mean is always the n times p. So for 50 trials and a 56% chance of success, we have 28 is our expectation. We expect 28, what is this? 28 people out of the 50 voters to favor the candidate on average. Okay, if we did enough of these trials. The standard deviation is the square root of n times p times q. And in order to do that, I'm going to have to go to a calculator. So let's do this. Different problem here. Square root of 50 times 0.56 times 0.44 equals 3.50998. So we'll just call that 3.51. Okay, but I'll store that in the memory and we'll clear that. So back to here. So that's approximately 3.51. Next step. Write the problem in probability notation using x. So we want to find the probability that fewer than 28 favor this candidate. So we want p of x less than 28. Well, now we have to do step 4, which is rewrite the problem by using the continuity correction factor. Now here's the deal. When you're talking binomial stuff, you can't have 28.2 voters in favor. You can't have 28.9 voters in favor. You can't have 27.3 voters in favor. Yet all those values are possible on a normal distribution. So how we correct for that fact is we set borderlines. So here's our expectation, which is 28. It's right in the center of the distribution, but 28 begins at 27.5. and it ends at 28.5. So this whole area in between 27.5 and 28.5 belongs to 28, and that area is the probability of getting a 28, or having 28 voters. Now the question, though, did not ask for what is the probability that exactly 28 favor this, or else we would be looking for the area that's in between these two cutoff values. Rather, it asked, what is the probability that fewer than 28 favor this candidate? And since 28 begins at 27.5, we are looking for the area to the left of 27.5. Hope that makes sense. Okay, so how are we going to find it? Well, we're actually looking for p of x less than or equal to 27.5. And to get that, we're going to convert that to a z value. So we're going to do P of z less than or equal to something. And the something that's going to go in there is going to be 27.5 minus 28 divided by 3.51. And we'll do that, sorry how messy that is, we'll do that on the ALEKS calculator. So parenthesis, 27.5, whoops, 0.5 minus 28, close parenthesis, divided by, and since I stored it, I'll just recall it, there it is, equals, and that is my z-score for that 27.5. Now I want to the left of that, so I use this button here, which gives me the area to the left of my z-value, that is the cutoff value. And now I hit that, I hit equals, and my answer is 0.44336. Now I can't put that in here because that was an earlier problem, and I chose to redo the video, but that's how you would do it. We're now going to do this one. A multiple choice exam consists of 80 questions. Actually, let's go here and scroll down. Consists of 80 questions. Each has a possible choice of A, B, C, D, or E. So there is a 0.2 chance of success in picking the right answer, a 0.8 picking it wrong. And let's just check to make sure that we're allowed to use it. Which one's smaller? P. So we'll check, is n times p greater than or equal to 5? That's our check we have to perform to make sure we can use a normal approximation of a binomial. So 0.2 times 8 is 16. So we're good. 16 is certainly greater than or equal to 5. And that's our expectation. So mu is 16. That's the center of our distribution. We need to figure out the standard deviation. The standard deviation is the square root of n times p times q, and we'll do that on the ALEKS calculator. It's going to be 80 times 0.2 times 0.8 square rooted. Actually, you could almost do that in your head, couldn't you? Except I don't know what the square root of 80 is, so that won't work. Okay, let's go there then. It's about 9, so it's about 9 times 0.4. So it's like 3.6 is my guess. Here we go. So we're going 80 times 0.2 times 0.8, enter. I said 3.6, look at that. Pretty close, 3.57. I'm going to store that. Now, the next piece is I need to do the correction for continuity. I need to convert this. We want to find the probability that a student will get at least 17. Well, at least 17 is 17 or more. So we want greater than or equal to 17. Whatever the z-score is for 17, but it's not 17. It's actually, where does 17 begin? At 16.5. Where does it end? At 17.5. So it would be helpful here probably to draw a picture. So I'll do that. We want to know at least 17. So 17 begins at 16.5 and ends at 17.5. This is all 17. 16 begins at 15.5 and ends at 16.5. So 17 is this area, but we want at least 17, so 17 or more. So we're interested in the area to the right of 16.5. 16.5 is included in 17. So now I need to convert 16.5 to a z-score. I'm going to do this all in one big ugly step. I'm going to say, because it's a right-hand distribution, I'm going to go 1 minus the p of z, and since that's finding me the area to the left and I want the right, that's why I did the 1 minus, and then I need the z-score of 16.5. So I'm going to do 16.5 minus, what was my expectation? 16, close that parenthesis, divided by, recall, 3.5 something, 5.6, 5.7. Okay, and that's that. That'll give it to me. This will find me the z-value for 16.5. This will find me the probability, or the area under the curve to the left of 16.5. And so subtracting that from 1 will give me the area to the right. So my answer is 0.4444. We need at least 3, so 0.444 is my answer. And that's it. Alright, I think I'm probably out of time. Yeah, so that'll be it for this one. I'll do another one maybe on another video. Bye.